Hi guys, we're at the very last lesson of Physics 20 through all of this COVID learning, and it's on something called the Doppler effect, which really is quite interesting to me. So we're going to start with a YouTube video from a show called The Big Bang Theory. Don't know if you've heard of it, but this is Sheldon trying to explain his Halloween costume.
Does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
All right, so there's Sheldon giving you a brief explanation of the Doppler effect. So the Doppler effect is when the frequency appears to change because something is coming closer to you and the waves get squished together. So I've got a visualization of this. We can see the red dot. Pretend that's you in your car. The best way to talk about the Doppler effect is about photo radar, I think. So if the car is getting closer to the police officer, the white lines are the waves, the wavelengths of the sound waves that your car would produce. Or when the photo radar is being shined on you, the radio waves that are bouncing off your car. As you have a speed going towards the cop, your waves are being squished together. But you can see behind the red dot, the waves are being, spread apart further. If I just stop this, the waves would all be uniform around the red dot or the car. So this is why police officers that are trying to do photo radar, they have to be straight on because they have to be able to take into account the Doppler effect. And if you're watching where these waves are from the side of a vehicle, you can't use that to judge how fast they're going. Okay, so if we can see the frequency of these waves, we can figure out the speed using the formula that I'm going to show you for the Doppler effect. So a little background, remember that frequency is the number of waves that pass a certain point in 1 second, oscillations per second. So the higher the frequency means more waves are passing a certain point per second, and lower frequency would mean less waves. So here's Christian Doppler, and 1824 is when he described this effect. He realized that when a sound source was moving towards the observer, i.e., your car moving towards the police officer, the waves would be squashed together, increasing their perceived frequency. So if the waves are squished together, then it looks like more waves are happening per second. A similar effect will take place when the source moves away, so the waves are more spaced out. They're kind of lagging behind and spacing out, which would cause a lower perceived frequency. The true frequency is not going to change. If you were doing photo radar on this car and it wasn't moving towards or away from you, the frequency of waves bouncing off the car would not change. But since it's moving towards or away from you, those waves get squashed together or spread apart, and the frequency happens more frequently or less. Just a random fact about this guy. He was a really small man and he was really weak, so much so that he required sick leave after finding teaching a very strenuous job, and it contributed in part to him becoming a scientist. His father's work, stonemasonry, was just way too physical for this little tiny man to handle. All right, here we have the mathematical representation of the Doppler effect. There's a lot going on. It looks quite crazy, so let's break it down piece by piece. First thing we have is we have frequency in a couple spots. So frequency with the subscript D. This I remember by underlining the D in perceived. So it's the perceived frequency. So it's the frequency that the photo radar is getting after those waves are squished together or spread apart. Okay? The S is the actual frequency of the source. Okay? Now, V always stands for speed, so we have VW and VS. So VW is the speed of sound in air, and Vs is the speed, the true speed of the source. So this is what they would be calculating for when they do photo radar. What is the true speed if it's 24 degrees outside and speed of sound in 24-degree air is this, and we know that the frequency of the radar that's bouncing off the car is this, we can calculate for the speed that the car is going. Okay, so this plus minus thing, you just have to memorize this. Okay, so when the source moves towards the observer, so when you're coming up towards a cop, you're going to use subtraction. When you've passed that cop, they turn around and they put their radar on you and you're going away from them. The waves are spread out. Away means at. So memorize this. Towards is subtraction. Away is addition. And the way that I remember that, away, add, both start with A. You just have to memorize that. Okay, so let's jump into some examples. A police car has a horn with a frequency of 220 hertz. The speed of sound is 340 meters per second. In this example, remember speed of sound always changes based on air temperature. And the car is moving 120 clicks. Determine the perceived frequency of the horn when the car is moving towards, subtraction, and away, plus. So we're doing the same numbers in our calculation twice, but one of them is going to have a minus in the bottom and one's going to have a plus. So let's figure out all the stuff we have here. The police car has a horn with frequency 220. The actual frequency of the source is 220 hertz. The speed of sound, VW, is 340. And the car is moving at 120 kilometers per hour. You guys know what to do with this number. We've got to be in meters per second. Kilometers to meters get smaller, so that's the division by your magic 3.6 number. And I am getting a repeating decimal here, 33.3 repeating meters per second. So get that on your calculator right now. So the whole number is sitting there, and you can use the second answer function in your calculation. So that's the actual speed of the source. And we're looking for the perceived frequency. So remember that D is what FD stands for. That's our question mark. So that's what our formula is arranged for. So this is a straight substitution. Let's start with part A. Here's just the formula written out. And I like to use the square brackets. It's just easier for me to visualize in my head. I'm doing towards, so I'm going to do a minus down here. Okay, I'm going to sub all my numbers in. Perceived frequency is what I want. The source is 220 hertz. The speed of sound in air goes in two places. That's a little different. We've never really seen that happen in equations before, but it does happen in this one. The subtraction is super important because it's towards you, and then goes that repeating decimal. So how you put this in your calculator, I would do it piece by piece because you're going to need a bunch of brackets if you do it all at once. You need to tell it that that's in the denominator. Okay, so go 340 divided by bracket 340 minus your answer for the repeating decimal, bracket. Get an answer for that whole square bracket and then times it by the 220. So pause the video for a second, put it in, and see if you can get the answer of 244 hertz. Perceived frequency of 244 hertz, which would make sense. The true frequency is 220, and if this object is moving towards the observer and those sound waves are getting squished together, then those sound waves are happening more frequently, so a higher frequency makes sense. What would we expect to see happening when they move away? Those sound waves spread apart. We would expect a number that's going to be lower than our true frequency, so lower than 220. So let me do the same calculation. I'm literally just going to copy this step here, but change it to a plus sign. That's all I'm doing. You don't have to use square brackets. I'll do this one with round just so you can see it in a different notation. Plus this time. Those double brackets are important there. If you're trying to do this all in one step, you're kind of playing with fire. Use the power of your calculator to use the previous answer in your next calculation. And the nice thing about the Doppler effect is if you really understand what's going on, you know if your answer makes sense. You know that 200 hertz, when the object is moving away from you and the sound waves are spread out, makes sense. It's less than the true frequency of 220. Which is exactly what we would expect. Now, when does this formula get a little more complicated? You could probably imagine that if we're solving for something in here, that's when the algebra can be quite intense. So let's do an example like that. Here, it's from 437 in the textbook, number 18. How fast is a sound source moving toward you if you hear the frequency to be 580, but true frequency is 540? The speed of sound in air for this question, we're going to use 350. Express your answer in kilometers per hour. So let's go through and let's underline a few important things. It's moving towards you. You just have to memorize that that means subtraction. We're looking for how fast is the sound source. So we're looking for speed of the source. You hear the frequency to be 580, but true frequency is 540. So let's write down what all of this is. The perceived frequency is what you hear. That's the 580. The frequency of the source, the actual frequency, is 540. That makes sense. The object is moving towards you. The sound waves are squished together, so they occur more frequently. Higher frequency is what you perceive in your ear. This is like when an ambulance is coming towards you and the siren sounds like it's going really, really fast, and then it goes away from you, and you know that change in sound that you hear and it goes slower. That's the Doppler effect that you're hearing. Okay, so that's what's happening here. And we know towards, so we know we need to minus, and we know the speed of sound. And some formulas will use VW, some will just use V. I'm going to use just V for this one because I think that's what's on our physics formula sheet. So that's the 350. And we're looking for the speed of the source. What is this actual speed going to be of this object? So let's write down the formula. So here I'm going to use V instead of VW. Towards, I'm going to put minus. Now, if you want a real challenge, you can try rearranging this right now for VS. It's quite a bit of algebra. So I'm just going to do the plug and chug method. I'm going to put all my numbers in here. 580 is my perceived. 540 is my actual frequency. Speed of sound is 350. That number pops in the equation twice. And VS is what I'm looking for. So how do we solve something like this? I'm going to kind of break the rules of physics here, and I'm just going to write the decimals that you should get on your calculator just so you can learn this concept. But really, you would just do all of this work. You wouldn't write any of it down in Physics 30. You would just write your final numbers down with proper sig digs. So the first step for algebra. The 540 here is multiplying by the big bracket. Since VS is in the big bracket, I need to get the big bracket by itself. So I'm going to divide both sides by 540. Okay, that's the first step with algebra. I get 1.074, and I'm just going to say dot, 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 because there's more numbers on my calculator, is equal to what I have left over here in the bracket. Now, the bottom of this is a binomial. Whenever we do multiplication of binomials, we have to consider the distributive property. So I'm going to make sure that's in a bracket. Otherwise, it's easy to forget to distribute. Why do I need to distribute? Because I am multiplying this whole bracket up. So I need to go 1.074 times this whole thing. Okay? So this is where you might want to store the 1.074 number in your calculator as x, and then you can just use it in multiple calculations. So here's the distributive property. It needs to multiply by the 350 and the negative VS. So that would make, messy numbers that I have to keep track of, right? The other thing that you could do, and what I'm going to show you here, now that's naturally what we would do with algebra. Since the numbers are so nasty, I'm going to show you a shortcut. That's multiplying, right? I can divide both sides by this number. And it will cancel. This just means you have to keep track of less numbers in your calculator. Okay, so just 350 divided by the answer that's sitting on your calculator right now. Let's find our work here. Okay, so 350 divided by that, I'm getting 325.86. On this side, I've just got the bracket left. Now my ultimate goal is to get VS by itself. So if I've got 350 in front here, I can minus it. But keep in mind, this gives me negative VS equal to negative 24.137. Now, what's the algebra to get rid of the negative? You can just drop it, but you need to understand why. It's really a -1 multiplying by VS. So if I want to get rid of it, I would divide both sides by a -1. What does dividing by a negative do? Switches the sign. That's literally it. So VS is just equal to the positive version of this, which is naturally going to be in meters per second. And our last step, if we reread the question, it says express your answer in kilometers per hour, is I'm just going to take this decimal on my calculator, multiply by my conversion factor of 3.6, and I get the speed of the source to actually be 86.9 kilometers per hour. So this might be an actual question, like the speed limit is 70 kilometers per hour. We use the radar, we hear the horn, we see the sound waves squished together or pulled apart. We do all of this calculation and find out that they were indeed exceeding the speed limit at 86.9 kilometers per hour. Okay, one more question. You can try this one on your own if you'd like. It's a little more challenging. It talks about the speed of sound in air at 350 meters per second. How fast would the source be moving towards you if the frequency that you hear is twice the true frequency of sound? What frequency would you hear if it had been moving away from you? So here's, part A. This question here in blue. Okay, I'm going to call this A. It says that we need to figure out how fast the source is moving, so same calculation that we just did, but they aren't telling us the true frequency and the perceived frequency. They're telling us a relationship between them. So we don't know what the true frequency is, but we know that the perceived frequency is double that. Okay, so in my formula here, I'm solving for Vs, and I do have information about perceived and true frequency. I know that whatever this one is twice as big. So I can pick whatever numbers I want. I could say, the frequency of the source is 500 hertz, which would mean the perceived frequency, double that, would be 1,000. But ultimately, whatever numbers I pick here, remember that the first algebraic step is to divide by Fs. So if I said this was 500 and this was 1,000, what would 1,000 divided by 500 give me? It's always going to give me 2. If I said this was 10 and this was 20, if I divide them, I get 2. I'm always going to get a 2-to-1 ratio because one is twice as big as the other. So the smartest numbers to pick are smaller numbers. I don't have to go with realistic frequencies like 500. I can go with my original frequency to be 1, and since the other one is twice that, 2. Why is this nice? Because math with the number 1 is really nice. Then I can pop in my 350 meters per second. This was towards, so I use subtraction. Now the 1, I don't have to do anything with that. Really, I don't need the brackets at all here. I can start by, and I'm going to combine 2 steps that we did in the last question to learn this into one shorter step. The 2 and the denominator can flip-flop. Just like when we would isolate in V equals D over T, we'd isolate for T, we just flip the V and the T. Same idea. I can put the 350 minus Vs up, and I can put the 2 down. I've just flopped locations. That algebra only works because I'm not adding anything onto this side. Okay, it doesn't work in that case. So what do I have here? 350 divided by 2. I've got 350 minus Vs over here. I got to isolate Vs now. That gives me a negative Vs equal to negative 175. Or if I divide out the negative 1 to make Vs positive, I get 175 meters per second. That's the true speed of the source, which I could give you in kilometers per hour as well. Now, all of that work was for part A that was talking about the object moving towards you. Part B says what would happen to the frequency you hear if it's moving away. So away means we're going to do plus. but the frequency is now not going to be double. That's only the perceived frequency when it's moving towards you and the sound waves are squished together. If it's now moving away from you, we don't know perceived frequency. So in our formula, we know V, we now know Vs, we don't know the source frequency, and we don't know the perceived frequency. So we're not going to get an answer for this that's like 200 hertz. We're not going to know a final number. We're going to know a relationship. That's like the initial question that said twice as the frequency you hear is twice that of the true frequency. We're going to have some sort of comparison like that, twice, triple, quadruple, something like that. So all we can really fill in here, we can't fill in any of this. We know the speed of sound is 350. And we now know that 175 is the actual speed of the object. I put a plus sign in there because now we're going away. So if I figure out that bracket, and remember this bottom part you better bracket or do in a separate calculation on your calculator. I'm going to get, a decimal on my calculator. But ultimately, if I math frac it, it's Fs times 2/3. What is that saying in words? You need to be able to translate what the math is telling you into words. That's telling me perceived frequency. So the frequency that you would hear that's what we mean when we say perceived frequency. When the object moves away, is, well, what is this? This is multiplying. 2/3 times the frequency. It is 2/3 of the source frequency. That's what this question's saying. This is when physics gets a little deeper. You aren't actually just subbing numbers in and showing that you have math skills. You're using your math skills to say something without knowing all of the numbers. That'd be 2/3, which makes sense when something's moving away from you. The waves are spread out more, so it should be smaller than 1 time the source frequency. So although this was originally intended to be used for sound waves, which is the main application, like the sound of an ambulance siren when it's coming towards and away from you, great example, or Sheldon in that clip from The Big Bang Theory, another great example. It does apply to other waves as well, like light waves. And when we're dealing with light, the change in frequency is usually related to the wavelengths. So with light, you've got the light spectrum there, Roy G. Biv, and a red shift is when something that emits light, like maybe a star that you're looking at in our universe, is moving away from you. That means that the frequencies are going to be, if it's moving away from you, spread out. So you can see the red wave there has longer wavelengths than the blue wave, which the frequency is squished together. So the wavelengths are shorter. That's going to give you different colors called a red shift and a blue shift. So what this tells us in our universe is that the light from distant stars, if it's emitting a red shift, this leads us to conclude that the universe must be expanding. Those stars are moving away from a central point. Okay? Interesting stuff if you're interested in our universe. Some other interesting things to wrap up Physics 20 is the sound barrier. So, as the speed of sound in air at a particular temperature is fixed, it's possible to go faster than this speed, like Indiana Jones with his whip, or a jet plane, or a wet dish towel. Everybody's been on the receiving end of that painful snap, I bet. These move faster than the speed of sound. So that snap that you hear from a dish towel or a whip or a jet plane is actually breaking the sound barrier. Okay, so basically we're just saying here when the speed of sound is greater than the speed of the object, your sound that you hear will be a higher frequency. That's the Doppler effect. Okay, that's cars. Cars are not exceeding the sound barrier. So when the speed of sound is bigger than the speed that the object is going, the frequency is squished together. When it's exactly the same, so if you are in an airplane and it's going the speed of sound, there's this buildup of wave fronts that occurs. So they get squished together so much that they kind of end up like one on top of each other in front of the airplane. This is like a high pressure system that the airplane has to overcome. It's also called Mach 1. And this increase in pressure can sometimes cause a cloud to form. And once they break that sound barrier, you hear that loud thump. Or if it's a whip, you hear that snap of the whip. Here is where we take the speed of the source and it's greater than the speed of sound. That's when you're going to hear that sonic boom or the snap of a whip, because the end of a whip is going faster than the speed of sound at that temperature. Here's kind of a picture of that buildup of pressure, and it's just showing you that. There's a YouTube video that I'll attach for just for your interest. It's really just some cool stuff about supersonic Mach 1 breaking the sound barrier. So you can watch that if you like. And your last assignment for this is going to be a unit assignment that I attach on my website. But remember that we only did 3 lessons in this unit. So a lot of those questions you're going to omit, and you're going to have to read on the website which questions those are. An answer key is posted. Make sure that you're showing all of your work, and let me know if you have any questions about these practice questions. It's really been a pleasure teaching you guys, even though we were only in person for a couple months. It was really nice to get to know all of you. Thank you for your hard work during COVID, and hopefully we can see you next year. I know we're all really itching to get back into the classroom like normal, which might not happen, but hopefully we can be together in the end, even if it is a few days at a time. Thanks, guys. Let me know if you need any help.